I usually have office hours after class, but I'm doing a seminar here this morning, so I will be available for office hours at 11 up to 2:25. If anybody wants to meet me at other times, please let me know after the lecture. I'll have regular office hours again on Wednesday. I know there will always be questions, and I'm always happy to try to answer them. So, in the last 4 lectures, we took a tour through lipoprotein metabolism, and its relationship to atherosclerosis, the way VLDL and LDL participate in that process, and how HDL affects against that process. As you recall, I hope, many cases of our understanding of mechanisms involved in lipoprotein metabolism arose from studies of genetic disorders. So you remember familial hypercholesterolemia, LDL receptor defect, dis-beta lipoproteinemia with the ApoE2 homozygous defect, Angier disease with the MTP defect, beta-cytosterolemia with the ABCG5GA defect. Those are important clues to understanding the biology that arose from clinical observations and genetic analysis in families that carried those mutations. So it's a good example, and this is certainly true in many other areas of biology as well, that to have that kind of a clinical perspective and understanding of genetics can lead to important insights. So as a MD who is interested in all of those things in genetics, I felt, and I think and my colleagues in this course agreed, that it would be worthwhile taking this lecture, to review some principles of genetics as they apply, in this case, to metabolic disorders. And this is also in part because we are really in an amazingly rapidly advancing state of knowledge about the human genome, starting with the Human Genome Project 12 or 15 years ago. This field is moving extremely rapidly, and for those of you, either those of you who are interested in science, hope we all are, and those that may be going on to clinical careers, you will be seeing more and more information that is coming from studies that originate in genetics. And it's very important to be able to cross that line between studying the genome and knowing how it works, how it impacts biology and health. So I'll be giving you some basic principles, and some of you who have had genetics or know genetics will, I think, know some of the major points that I'll be introducing. But I do want to have everybody start on the same page, and I'll show as we go along how these genetic approaches can be related to biological discovery. So I mentioned the several cases of what are monogenic disorders, single gene disorders that can affect, in this case, lipid metabolism. But there's many other examples, and these monogenic disorders, single gene disorders, are also called Mendelian. Mendelian after Gregor Mendel, who was the discoverer in the late 1800s of genetic transmission, even before we knew that there were genes, by studying the segregation of traits of pea plants, of all things. So here we have examples of single gene disorders. Sickle cell anemia, one single genetic mutation causes this disease. Familial hypercholesterolemia, again, it's a single genetic defect in any given patient, but there's over 1,500 individual genetic variants. I mentioned in the earlier lecture. Any one individual may have one or another of those genetic traits. And remember, there's 5 classes of disorders that all cause that trait. But in any given family, it's a single gene with what's called high penetrance. That is a single genetic trait that can cause a major phenotype. In this case, it's called autosomal codominant. That is, even a half dose, even a single dose, ordinarily you inherit 2 chromosomes, and you inherit 1 with that trait. That's still enough to cause disease. Huntington's disease, a very classical, severe inherited disorder for which we don't have treatment. Things like colorblindness and cystic fibrosis, another classical example. So these are all inherited diseases that are Mendelian, single gene, monogenic, highly penetrant. But most common diseases, and that is the kind of metabolic conditions that relate to the biology for this course, are complex. In fact, I'm sure I've convinced you, the deeper you go, even in lipid and lipoprotein metabolism, you encounter greater and greater complexity. And as that complexity increases, you have to consider many factors that contribute to that are regulated in a way that performs, hopefully for most of us, in a coordinated way. And this ultimately relates to multiple genes, which affect multiple pathways. And those genes and genetic pathways don't operate like the Mendelian diseases I mentioned, which will cause, those genes will cause disease under any circumstances. These traits that have relatively low penetrance are influenced by environmental conditions. They don't cause disease or trait in all cases of affected individuals. They require something in the case of lipids like diet, exercise, even stress, can interact with the genetic underpinnings of the disease, with these common traits, which involve multiple genetic traits. If they are familial, they create predisposition to disease. They don't necessarily always cause a disease. As I mentioned, a very large environmental and behavioral component. And this is where the role of diet comes in, exercise, etc. People that have genetic traits that make them susceptible to high LDL cholesterol don't necessarily have a single LDL receptor mutation. They may have other traits that are less extreme that can be modified successfully. So again, this is basic stuff. So again, some of you may know this, but just to be sure we know what we're talking about. When I first heard the word SNPs, I thought it was something that happened when you use scissors. But SNPs are single nucleotide polymorphisms. I'll show you what those are in a second. That can be analyzed in the laboratory and can be used to track predisposition to disease and many genetic traits. So the idea is, and the way these are discovered generally, is by taking DNA from different individuals and sequencing either the whole genome, nowadays it's possible, or portions of the genome, to identify sequences in which there is a single nucleotide, A, G, C, or T, which varies across individuals. And that's the SNPs, single nucleotide polymorphism. And here's an example just to illustrate that individuals in a single region of the genome can carry either a G or an A, adenine or guanine at this locus, the G being the rare allele. The allele is the SNP that comes from one chromosome, and other individuals can carry the rare allele is a G in this case, and the common allele is the A. So there are individuals that have one or another, either green or red. In the normal population, most of them are red. Most of them carry the A allele. So this is a population where there is variation, and some people carry the trait, genetic marker, the SNP, others don't. But in a diseased population, it can be found, again as an example, that the green allele, the G, is overrepresented. There's a higher prevalence of this minor allele, this minor variant, these are all saying the same thing. SNP is carried on a chromosome that's an allelic genetic locus. All of those are saying the same thing. The green SNP, people with green SNP, are overrepresented in the disease population. And so that higher than expected incidence of this allele, this trait in the disease group, can be statistically analyzed to show that there is an association of that trait with the disease. So it's very highly statistical. And so in this overall area of genetic science, we move from something that you can tell just by eyeballing it, looking at a patient who has xanthomas or some other obvious conditions such as very high cholesterol. You don't need statistics for that. But here it's very statistical. And we're not going to try to deal with statistics today, although I hope all of you interested in science will learn some statistics or have learned some statistics. But the general idea is really to look for an association of an allele with the trait. So in the old days, when this field was started, we thought we knew where to look. When we looked at high cholesterol population, we thought, well, let's look at the LDL receptor gene, and we did find variation. But as I'll show you, there's a lot of other genes that can influence cholesterol or any trait that are not the ones we think are obvious. And so the fun and the excitement in this field has been to go beyond the obvious, looking just under the streetlight, but looking for something. Looking for something that, here are your keys out here. The way you can find it is by turning on all the lights. So that's a kind of a metaphor for a genome-wide approach. That is not imagining that you know where to look for a single gene that may cause a problem, but because we know multiple genes can be involved in many traits, we open up discovery. This is where we discover new stuff. And that's fun, and it's also informative and can lead to new insights for disease. So this is called a genome-wide association study. It's looking at all the SNPs, not just SNPs in certain genes. And now this is some of the earlier technology, but it's basically the same approach. Is on a little chip. You can array now millions of SNPs. There are indeed millions of SNPs in our genome, and it's just opened things up enormously. And then one can look for associations across the entire genome with disease. And this is an illustration of how that analysis winds up looking when you display it graphically. This is, for reasons that you may recognize, called the Manhattan plot. You see some skyscrapers here. These skyscrapers are places where there is a strong association across the genome. So this is a display of all the chromosomes. There are 22 plus X and Y, and they're shown in alternating blue colors here, 1 through 22. And the places where there is a strong association of a single SNP or a region of SNPs with a trait, in this case, type 1 diabetes, diabetes that is due to lack of insulin production. That association is quantitated by a statistical value called the p-value, and using the minus log p-value, you get a number that you can display quantitatively. So this, don't worry about statistics, just know that this is a index, this number on the y-axis is an index of the strength of the association. So if you hopefully follow me, you can look across the genome and see that there's 1, 2, 3, 4, or 5 of these skyscrapers that rise above the background in terms of statistical significance. And they represent specific sites on the genome that in some cases have led, as I'll show, to discovery of genetic associations that have told us about previously known were associated with disease. So there's been many such studies, and this lecture isn't really designed to have you understand all of the work that's been done in this area. I wouldn't have time to do that. And so I'm taking some illustrative examples, some of them from a number of years ago. Now, I can't believe this is already 10 years old. I'm going to show you, but this basically illustrates many such studies over the last 10 or 15 years. This one from England, the Wellcome Trust, I'm not sure, as you can see the names of these. Here's the Manhattan plots and the p-values here, but now we're looking at not type 1 diabetes only, but we're looking at other traits that are thought to have a genetic contribution. In fact, most conditions do have a genetic contribution. So this is bipolar disorder, coronary artery disease, heart disease, Crohn's disease, intestinal disorder, high blood pressure, hypertension, rheumatoid arthritis. Here's type 1 diabetes again, and type 2 diabetes, which is the more common form of it, insulin resistance. And you see patterns basically here. But what I want to zone in on, which is relevant to other work that you'll be hearing about during this course, is the study of the genetic association with type 2 diabetes. And again, this was an earlier observation. It's been extended, but the basic approach, I think, is what I want you to understand. Not know what all the findings are, because there's hundreds of them now. But this shows for this trait where the p-values, where the strength rises above this dotted line. The dotted line is a threshold for meaningful associations where the strength is so strong that it can't be explained simply by chance. And so what this illustrates here is the top 10 list for this study, which has been corroborated now in many other associations. One of the things that has to be done in this approach involving large numbers, thousands of patients and statistical associations, is some degree of validation of an observation, just to make sure that you just haven't come across something by chance. And that can be done by repeating it in different populations or doing studies in the laboratory to show that what the gene you discovered actually has a causative role. Well, these associations with type 2 diabetes have been replicated in these top 10 loci. And the one I'll mention as an illustration down here is SLC3088. So these all have these obscure acronyms, these things you don't necessarily need to know where they come from. This is a solute transporter that did not have a known function, but one step led to another, and it was discovered that this gene, in which this variation, this abnormality was associated with higher risk of type 2 diabetes, is a transporter that's important for zinc uptake. So why is that relevant to type 2 diabetes? Well, here's a transporter inside a vesicle in the cell, and this is the beta cell where insulin is secreted. And that transporter is responsible for moving zinc into these vesicles where insulin is being transported and organizing the insulin into a structure that can then be capable of being released when there's a second signal coming from a calcium channel, and that release allows insulin to be secreted. So that's a really important function of a gene, and the genetic variations that were discovered influenced the function of this transporter, so it resulted in reduced zinc transport into the vesicles and impaired insulin release, and that is one of the hallmarks of a process whereby the pancreas can't keep up with the glucose supply, and it eventually it runs out of insulin secretory capacity if this zinc transport mechanism is disrupted. So this is something that is illustrative of a discovery that has relevance to biology and disease. So what about lipids? I spent the last 4 lectures talking about lipids, and so that's been one of the most widely studied traits using the genome-wide approach, as has coronary artery disease, CAD. And so there's been many GWASs of lipids. In fact, there's one study that is now underway that involves data from something like 1 million people around the world. So it's because everybody measures lipids, and there's a lot of studies, a lot of clinical settings where lipid data are available along with genetic data. So it's provided really a tremendously rich source of material to do these genetic analysis. So this is a study from a few years ago in which 3 traits were analyzed, which are generally done in the clinic: LDL cholesterol, triglyceride, and HDL cholesterol. And here are SNPs. These are numbers that tell you what SNP we're talking about. Again, the SNP doesn't matter. What matters is the gene or the locus where that SNP is contained. And then here's the numbers of people that are involved in studies. Again, LDL cholesterol, hundreds or thousands of people, triglycerides as well. And here is a p-value. So let me show you the example at the top is the LDL receptor locus. Again, not surprising. That's where we started in terms of genetic disorders, but these are not the variants. These are not the genetic mutations that disrupt the processing or the structure of the LDL receptor, those 5 classes. They're out of the picture here. These are other variations that affect mostly the regulation of the LDL receptor. And look at the p-value. Those of you who know about p-values, if it's 10 to the minus 2, it's pretty good. 10 to the minus 3. This is 10 to the minus 262. That's on the scale that I was showing you before, that would be 262 on the y-axis. Enormously strong. And this corroborates that there's a relationship of those same SNPs to coronary artery disease, and that's a very strong message regarding causality. And I'll come back to that at the end of this lecture, is that if you see a SNP associated with a trait that you know has a relationship to a disease, and then you see that that same SNP also predicts the disease itself, that tells you that this is a meaningful connection between the trait and the disease, that the main variant that causes high LDL also causes coronary disease. That's very strong evidence. I'm not going to talk in detail about these other traits. I'll just briefly point out that you'll see a couple of familiar characters here. So in this case, it's not necessarily discovering new genes. We haven't talked about that. There's many of those, but that's not what you need to know about this lecture. This rediscovered the importance of a locus that has 2 genes of interest: ApoA1, which is an HDL protein, and ApoA5, which, you remember, modulates lipolysis by lipoprotein lipase. That emerged at the top of the list for triglyceride lipoprotein lipase. And then TRIB1 actually was a discovery. We won't talk about that. That was a new gene that was discovered through this genome-wide approach. For HDL cholesterol, look at this p-value. And it's gone higher than that. 10 to the 9, it's almost for science fiction to have something this high. 769 is just out of sight. That strength was associated with one locus, which is a cholesterol transfer protein locus. And you'll remember that CETP did modulate processes that regulated HDL. But I'm going to show you just one other example on the LDL cholesterol side. The second one on the list, just below LDL receptor, was a discovery. This wasn't really known to be associated with anything related to lipid metabolism. It actually had a stronger relationship, 10 to the minus 10, stronger than 10 to the minus 7, with coronary disease than even the LDL receptor. So this was a pretty important discovery that led to a flurry of research. And again, just for interest, I'll tell you what was learned about this. That locus encodes a protein called sortilin. And sortilin is a transmembrane protein that sits in the Golgi network of the cell. And it binds things. It has a lot of sites that just binds ligands. And it has been known to do a lot of shuttling of materials in and out of cells are through the cellular machinery, but never anything related to lipids. So I'm not going to go through the details. I realize there's only one part of the slide I want to show you, and that is that the sortilin itself, that protein was shown to bind to ApoB. That's what these data show. You don't need to understand biology here. Just that there was studies showing a very tight association of ApoB with sortilin, ApoB being the protein. That's what is shown by this series of lines. And then in mice, when sortilin was expressed, the gene itself was expressed either without any activity or with high activity, the red versus blue and the green in the middle. As you put more of the gene in, you've got this line shows greater and greater LDL uptake. There's less and less LDL remaining in the system. So this is, again, don't need to understand this completely, other than that gene discovery led to a new functional protein that binds ApoB and that clears LDL from the blood. So a completely different axis of the LDL receptor. So another example of discovery that's related to this course, both the lipid story as well as a topic I'll be talking about later in this course, which is fatty liver, which is related, obviously, to liver metabolism. A group at Dallas was able to measure in vivo in humans the amount of triglycerides stored in the liver. So the amount that's in the liver of triglyceride is important, because if there's too much, it can lead to fatty liver. We'll discuss that later, of course. And it can also promote the secretion of triglyceride into the blood. So here we have patients with something that just jumped up off scale here on this chromosome 22 that was highly associated with liver fat. And so that was the discovery of a gene called PNPLA3. It's a palatin-like phospholipase type gene. Palatin is a protein that is found in potatoes. That's how this name is devised. So this is, again, an example of how the genetic machinery that we have really came through a zillion years of evolution. And some of the genes, many of the genes we have are shared with plants, forms anyway. But it was shown to have a hydrolase activity. Don't need to know details of that, other than it is capable of hydrolyzing triglyceride. And this mutation, this variant, is in a region that's responsible for that enzymatic activity. And importantly, genes are present in the DNA throughout the body, but they're not always expressed in all tissues. The genes may be sitting there just minding their own business in tissues, let's say like the eyeball, but when they're in the liver, they get turned on. In this case, or the fat tissue, in this example, they can be turned on and become functional. And as I mentioned earlier, in this case, as many others, there's a strong environmental component. So the activation of the regulation of this gene expression of these tissues is dependent on environmental factors, particularly in this case, nutrition. So this is bringing us back to nutrition and carbohydrates, which you know from last lecture have a big effect on triglycerides. But there was another discovery that came from this, which is really kind of cool, and that is it's been known for quite some time that there are differences in the prevalence of fatty liver. Hepatic steatosis is again a jargony term for fatty liver, fat in the liver, which can lead to severe liver disease, cirrhosis, for example. And I'll just show you the gradation here from African Americans to European Americans to Hispanics, where nearly half of Hispanics have a predisposition to fatty liver. Yes. And this shows the frequency of the minor allele of that gene, this variant. I should say this is a DNA variant, as I should have said at the very beginning, obviously a DNA variant in the coding region is also going to affect the amino acid sequence. That's the fundamental biology. If you have a genetic variant in the coding region, it will affect the function of that gene. So here is that variant. Almost half of Hispanics carry that variant, almost 3 times as many as African Americans, and it's highly proportional to the prevalence of steatosis. So this can explain a genetic basis, nothing to do with diet or anything like that. In this case, it's a genetic predisposition that leads to this difference across these 3 groups. And just some interesting biology here. Here's PNPLA3, also called adiponutrin, which is stimulated adipose tissue by feeding. There's a similar gene, PNPLA2, adipose tissue triglyceride lipase, was studied by one of the faculty here at Berkeley, that is expressed in the fasting state. They both have the same effect, but if you eat too much and get this gene turned on, it causes more fatty acids to come to the liver, and it leads to some bad things, triglyceride synthesis, etc. So those are a couple of examples of discovery. This, what looks like a complicated slide, I'm going to sort of break down because it illustrates an important point, and that is that if you look across all diseases and all allele frequencies, so here are allele frequencies on the x-axis, very rare trait, very rare genetic variants, they're very common. To get a disease, and this y-axis shows the penetrance, basically, or the likelihood of having a disease. Here is a rare variant that can cause a Mendelian disease. That's the LDL cholesterol mutations in LDL receptor that are one of those 5 classes that can cause severe elevation of cholesterol. There can be rare variants with small effects in those same genes, but they're very hard to discover because if it's only 1 in a million and it's a very small effect, it's very hard to see. So it's easy to find these guys. At the other end of this extreme are common variants, and that's what we mostly have in our genome associated with common disease. But the effect size here is relatively small. So here are common variants. This is the prevalence, not here, here's the highly prevalent, small effect. So this is sort of the axis that most of genetics works on. Rare variants with big effects, Mendelian disease, common variants with small effects related to chronic disease. And that's really the point you should take away from this slide. Off of this axis, as I said, are the rare variants with small effects, and the common variants with large effects, again, sort of off that axis, are uncommon. There are very few examples of common variants that have big effects, and that's what makes it necessary in these complex traits to look at many thousands of people, because you need to get the statistical strength to show that association. So I'm going to conclude with a related use of genetics that is becoming really important in clinical medicine. I'll try to explain why that's true in just a minute. But first, let me take you through this, because it's going to take a little, hope you're all awake, because this is going to take a little thought to kind of get what this is all about. This is called the principle of Mendelian randomization. And the only reason it has that title is that the analysis that I'll talk about depends on having genes distributed in a Mendelian manner. That is, one parent gives one allele, one version of that variant, and the other parent gives the other variant, and then you inherit it in sort of a random way. There's no selection for particular variants. So actually, don't worry about that. Don't worry about the semantics. What I want you to understand is how this principle actually works. So here are the gene variants. And the gene variants can affect disease directly. Or you can have an association of the gene variant with the disease. So let's, again, talk about heart disease, what we're talking about. And you can test for the association of a genetic variant with the likelihood of getting a heart attack. You can also test for the effect of that same genetic variant on the biomarker of interest, that's LDL. And actually, talked about that when I showed you that slide with the LDL receptor and the sortilin variant. You can have a single variant associated both with disease and with the biomarker, LDL. This is called an instrument. And this really, all this means is that this gene variant has to specifically affect that biomarker. It can't affect anything else. So if we know a gene variant affects LDL and only LDL, then we can ask the next question, and that is, does the effect of that gene on LDL predict disease risk based on the relationship of LDL itself to disease? So this is known. This relationship of LDL and disease risk is known. And what's discovered is this relationship with disease and this relationship with biomarkers. So let me explain again how this works. So you take the observed risk estimate, that is how strongly this variant predicts disease, and compare it with the predicted risk estimate based on the effect of the genetic variant on the biomarker that itself has a disease prediction. Again, just hold that thought. I'll show you an example. The example I'll show you is PCSK9, a friend from previous lecture, which, as you will recall, is a protein that is secreted by the liver that targets LDL receptors to lysosomes for degradation. So you remember, here's PCSK9 being secreted, it binds to an LDL receptor, it moves into the cell, it directs that receptor to lysosomes, thereby preventing it from recycling to the cell surface, leading to a deficiency of LDL receptors and a high LDL. That's the normal function of the gene. But where it becomes informative in the genetic sense, and we've talked about this, is the loss of function. I know some of you, a little confused about this because it takes a little thought. This is a gene whose normal function is bad. So the normal function of PCSK9 is to raise LDL. So SNPs that actually damage the function of this gene, which cause less degradation of LDL receptors, improves the uptake of LDL and lowers the plasma LDL. So this is called the loss of function variant. And the genetics surrounding that loss of function variant fit very nicely into the scheme to prove that LDL is the reason for heart disease risk, because here are the variants that are associated with lower LDL cholesterol, 21 milligrams per deciliter. We can tell from other data that this degree of LDL lowering would predict a relative risk of MI of 0.8. That means the normal risk is 1. This is 20% less. So the normal risk is 1.0. This risk is 0.8. That's 80%. That means that there's a 20% protection from heart disease. Just, you got that. So lower LDL, less heart disease risk. Here is the actual association of this variant with disease itself. So this variant is associated with a 28% reduction in risk. And this is an independent analysis that has nothing to do with LDL, but look how closely these numbers match. And that's really the power of this technique, because it pretty much shows that you can explain this protection from disease simply by knowing the LDL. Now this number is actually, if you'll want to take it one step further, slightly better than this number. So the genetic association of disease is actually a little bit stronger protection than would be predicted by LDL. But the carriers have had this genetic variant all their lives. And so this protection is actually a lifelong protection versus data that are required for this analysis are really mostly in adults over a period of time to look at risk over several years. So a lifelong protection is shown here as being due to this genetic variant that it's quite consistent to lifelong lowering LDL being protected. So finally, there's a similar example of HDL. So you remember and you know that HDL is associated with protection from heart disease, very strong protection, such that if your HDL is low, you're at higher risk for heart disease. However, there's been some questions about the causality. Does low HDL really cause heart disease, or is it something that just sort of travels with heart disease, associated with heart disease risk, but itself is not causative. So a genetic approach has been used here as well. In a gene, like gene, don't ask me why, it stands for endothelial lipase. That's EL, it's on one of your previous slides. It's a gene that is involved with metabolism of HDL, hydrolyzed HDL phospholipids. It's on your list of genes that we know this mechanism for. And as far as we know, the only thing it does is affect HDL, doesn't have any other effects. So if there is a defect in this particular gene, this variant, it causes an increase in HDL cholesterol. That increase in HDL cholesterol is associated with protection from heart disease risk. Same idea. About a 13% protection would be predicted by the HDL effect. But then if you look at the real relationship of this variant to disease, 0.99, that's as close to 1 as you can get. It shows that there's no association of this variant with heart disease, despite the fact that it's associated with higher HDL, and exclusively with high HDL. So this pretty much is one of several lines of evidence. They pretty much put a nail in the coffin of HDL cholesterol as being causative. This is saying even if you have a high HDL cholesterol, it doesn't protect you. This genetic variant that causes that increase in HDL does not protect you from heart disease. So what does all this mean? So we can use this technique, and this is again getting into some of the research, but it's entering the clinical literature now. What it does is it's using genetics in a very powerful way to establish causality. And in the case of LDL, the genetic story is very consistent with the benefits of reducing LDL. Genes that raise LDL increase heart disease, genes that lower LDL increase heart disease. For HDL, that hasn't worked. And there have been several very high-profile clinical trials, one of which is still underway, attempting to raise HDL with drugs that have failed. Drugs that raise HDL have not really been shown to affect heart disease risk. So does this mean that what I told you earlier about HDL and its protective effects is wrong? No, it's more subtle than that. Where does this leave HDL cholesterol? Well, HDL cholesterol is associated with cardiovascular disease risk. That's true. Don't forget that point. There's a physical association. And there are mechanisms involving several effects of HDL in the artery, which we talked about, promoting efflux of cholesterol from bone cells, and blocking adhesion molecules, blocking LDL oxidation. All those things are true. So what's wrong with this picture? Well, what this is saying that simply changing HDL cholesterol, that measurement in the blood, isn't really the answer. It doesn't really address the primary mechanism by which HDL is operating. So HDL cholesterol, which is used in the clinic, may not be a measurement that reflects what HDL is really doing. So we may need more precise measurements, not of HDL cholesterol, but of some effect, such as, for example, the level of production of ApoA1, the HDL protein. That's not been studied genetically. So it may be that we need to find ways of really working at the mechanism in ways that may not involve raising HDL cholesterol, but really focusing on the factors that are really important in HDL function, such as ApoA1 production. And there's an industry underway now which is moving in that direction, away from drugs that raise HDL cholesterol to looking for drugs that raise things like ApoA1 that might be much more indicative of disease benefit. But studies like this have helped to show that HDL cholesterol itself is not a reasonable target for treatment. So that's all I'm going to say about genetics. I'll be available for questions for a few minutes now, and we have office hours later this week, just let you know.